Hi, and welcome to this, our first class with Charles. Welcome. Thanks for coming into our studios.
Oh, it's a pleasure. Thank you very much.
Well, of course, you'll have known that Charles and I did some colour science stuff when we were doing our Background Fundamentals course, which was shot in Vancouver.
Mm-hmm.
You are actually from Canada.
I am.
So that was home turf for you. We're actually here on my home turf now, but I'm actually not going to be primarily in the course this term. Charles, you're going to be doing that, though. We'll come in maybe at the beginning and end and just ask a couple of questions.
Good.
It's, you know, Professor, I get a treat.
And it's more fun. It's more fun.
What are we going to be covering? What are we starting with?
Well, I'm going to present this in a way that some people might think is the wrong way around. I'm going to do color first,
okay,
and then grayscale.
Okay.
You could sort of think of grayscale as being the foundation of color, but it's really more interesting to do the presentation the other way around.
So are we going to get geeky? Because I think that was the thing that people said. They loved background. That was a 200 level course. We're trying to pitch this at 300.
We will get geeky. We will absolutely get geeky. But the way that I like to teach these things, I like to talk about what I call the deep fundamentals. Okay. So in some sense, it's fundamental, basic material, but color is so complicated end to end that even the fundamental stuff is very subtle and very complex.
And just in super broad strokes, we will be discussing that fundamental stuff. And when it comes to formats, I guess, we'll discuss some HD and, of course, what I'm going to call cinema.
Yep.
But we're not going to get into like PAL and NTSC and...
PAL and NTSC are obsolete now.
Okay. So it's basically, we're either pretty much talking 1920 by 1080, what I'm going to call Rec 709, or general colour science stuff related to digital cinema.
Right. So 2K, 4K.
Okay. Well, I'm looking forward to it.
Me too.
We'll get started.
Okay, good. Thanks. We start the story of color in the dorm room of Isaac Newton in Cambridge in 1666. Now, this is the year of the plague in England, so I think of him as shutting himself off inside his dorm room, and he's a troublemaker. He's cut a hole in his window shade. He's admitting sunlight. It first strikes a lens. The most important part, and of course the center of his drawing, is the prism, which takes light coming in, sunlight, spreads it, and produces an array of different colors on this card sitting on the stand. So Isaac Newton figured out that within sunlight are some components which appear colored when separated by the prism. Well, Mike, being a very detail-oriented kind of guy, was not happy with just Sir Isaac Newton's sketch. Mike suggested, I'd like to see that in real life. So here we are in the lab, demonstrating separation of white light into all the colors using a slide projector, which was quite some trouble to locate, a narrow aperture in the image plane, which we constructed on the fly, and a prism, which is located about 6 meters back in order to produce enough dispersion. So the prism that we're using is one exactly like this, and it's located half a meter from the slide projector. So you can see what's happening is that the white light is dispersed by the prism and presents this rainbow on our white wall. You can see that we've got red, orange, yellow, green, blue, and these are the colors that Isaac Newton talked about when he finally, 30 years later, wrote this experiment up in his book. But he didn't stop with ROYGB. He went I and V, indigo and violet, because you can see that there's quite a range of blue colors portrayed. And in a few moments, we'll turn off the lights on me and you'll get a better sense of the colors that are displayed. And you get some notion from this diagram that yellow seems to be a unique color, although you can see here we're blending it across from red to yellow to green. But yellow, as I mentioned earlier, is a perceptually unique color by virtue of the way our visual system is wired up. Now, the other thing I'd like you to notice from this real rainbow experiment is no purple, because you go out into very deep and very intense blues, but there's really no color there that's got any combination of long wave and short wave, and it's those combinations with not much or nothing in the middle that creates the visual sensation of purple that's absent from the rainbow, because all of these colors have got a peak just at one wavelength. They've only got one lump in the spectrum. So let's now switch our lighting off to give you a better notion of the colors up in the blue range of the spectrum. So here's the spectrum without being interfered with lighting. And there's a couple of features that I'd like to point out to you. You can see that the brightest portion of the spectrum is in this range. In terms of physics, the power distribution is roughly the same all the way up and down the whole rainbow, but the visual sensation is brightest around here, and that corresponds to around 550 nanometers. And down here there is light below the red. That's, of course, infrared. And eventually, well, in our particular light source that we're using in this experiment, there's really no ultraviolet to speak of. But when Newton did this experiment, he did so using sunlight. So he would have been refracting infrared light as well as ultraviolet light, but we can't see that. And you may notice then this ROY, Roy G Biv, blue, indigo, violet. You're getting quite intense colors up here, but none of them can really be described as purple. The other little detail of Newton's sketch that I love is his use of a second prism lying behind the card. He's cut a little hole into the card, put a prism behind that, and because I have a second prism here in my hand, I can show you that phenomenon. He's showing you that once the light has been separated by the first prism, no further separation is possible. So here, if I had a wideband light source incident on my second prism, I'd display the whole rainbow. But because the light has already been separated into its fundamental components, there's no separation. I just repeat the same color. 30 years later, Newton wrote up this lovely idea where he says that, properly speaking, the rays of light, are not colored. In them is a certain power or disposition to stir up this or that sensation. So that's pretty much a direct quote from Isaac Newton. And what he's really saying is, color is not in physics. Color is in the eye and the brain. It's all about perception. Now, there is a link to physics, and to build a camera, that's what we need to explore. So we can nowadays measure the physical properties of light with an instrument like this Photo Research spectroradiometer. And this instrument takes light coming in. It has a small imaging system represented by the lens. It splits light into physical components having wavelengths between about 400 and 700 nanometers and gives us the amount of power in each of those bands. Now, I'm going to talk about the spectrum as being from 400 to 700 nanometers. That's the significant portion in terms of color vision. Now, a color scientist might go a few tens or 20s of nanometers beyond those intervals, but that serves our purposes. And also for our purposes, it's convenient to split into 10 nanometer chunks. So quantifying the whole visible spectrum takes 31 components. And in principle, you could achieve color display or color transfer from in front of a camera to the back end of a display by just sending those 31 power values across the whole spectrum. This would be called spectral reproduction. And it's completely theoretically valid. It's not very practical because 31 numbers is just, it's too many components to have per pixel. So we'd like to figure out a way to have just 3 components because we know that the retina of the eye has got 3 color-sensitive photoreceptor cells. So if only we knew what those responsivities were, we could do color in 3 channels. Well, of course, we all know that is how we do color. So the next step in our journey is to figure out what are those 3 channels. Now, to give you a notion mapping into a real camera acquisition scenario, or in this case, acquisition from a scanner, I'll use an example that I created about 15 years ago when I was living and working in the Bay Area in Silicon Valley. Now, I was a transplanted Canadian, so I picked up from a hike up on the hills above Palo Alto the closest thing that I could find to a maple leaf, which turns out to be the leaf of the liquid amber tree. And I picked this leaf up, took it back to the office with me, laid it on my flatbed scanner, pulled a scan, looked at it on my CRT display, and the colors didn't match. And I made a hard copy print on a color printer I had at the time. Those colors didn't match. I took the digital files, shipped them off to the company that was making 35 millimeter slides for me. They didn't match. And so the question is, why didn't they match? What is it that you need to do to make the colors match correctly? The liquid amber leaf will be our example. Now, take the first row of this diagram as our first attempt at building a set of 3 filters, loosely speaking, red, green, and blue. And our goal is to make filters that we place in front of the sensors on a scanner to parse out the red, green, and blue information from that optical stimulus. And if you hand to an optical designer the problem of building a set of filters to separate the wavelength intervals 400 to 700 in 3 chunks, the optical filter designer will probably use textbook filters that have got rather uniform response in the passband, rather rapid rejection outside that region, attenuating to a very low degree outside the interval of interest. So here I've drawn 3 filter characteristics with characteristics like the ones I've just mentioned. So the long wave filter, which you could loosely call red, is passing roughly from 700 to 600 nanometers. The middle wave, 600 to 500, and the long wave, 500 to 400. Now let's suppose that our leaf, which has got some red, some orange, some yellow colors, let's suppose, just for the sake of argument, that its orange reflectivity is very narrow band and its red reflectivity is very narrow band. Now, in practice, most of the objects that we encounter in real life don't have narrow band reflectance. They've got rather broad reflectance spectrum. But let's explore what would happen if they were narrow band. So we've got a red spectral line, very narrow band red component, a narrow band component around 620 nanometers that appears orange. And if we had such a stimulus on the scanner and pulled a scan using those filters that I've described, there's a problem. The problem is that each of these 2 optical stimuli produces RGB values, in this case 1, 0, 0. Same triplet of RGB values comes from both of those stimuli, but we see those stimuli as being different. So we've built a scanner that doesn't work. It can't distinguish orange and red. So we think to ourselves, well, we'd better go back to our filter designer and get another set of filters. And I guess what we have to do is build a set of filters that's got better capability to separate those wavelength bands. So maybe we need a filter that's got narrower spectral characteristics. So let's build a set of filters in our second try that centers on 620, just for the sake of argument, centers on 540, centers on 450. And now let's retrofit those filters in our scanner, put the leaf back on the scanner, pull a scan with the same orange and red stimuli. I should say stimuli that look to our eyes to be orange and red. And when we do so, in my admittedly contrived example, the orange falls through the cracks. It reports RGB values 000, indistinguishable from black. This scanner doesn't work. And you can see that we're creating a scenario here where we're going to have to work away at building scanner, 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 scanner until we get it right. And our criterion for determining whether the scanner works or not is exactly this. Now, this part is very subtle. The scanner works correctly when it reports different RGB values for optical stimuli that we see as being different colors. That's the criterion for success in a scanner. Now, that is kind of a test, but it's not a recipe. It doesn't tell us how to build the scanner, what curves to use. It just tells us whether we've got it right or wrong. There was a very interesting set of experiments done in the late 20s where the color science community in the world at that time got together to try to figure out what those curves were. And the curves are those curves which in some sense mimic the behavior of the eye. And those curves end up being the curves that I show you here in the bottom row of this graphic. Now, these curves later on were discovered to be very, very close to the physiological responses of the 3 cone cells in a human retina. Now, it's another question which we'll address in a few minutes. How close are they? Are different humans, do they have different curves? Do they have different responses to color? We get to that in a moment. But the short story is this set of 3 curves mimics the behavior of vision. And if we place our orange and red and yellow leaf under these curves, the RGB values that are reported will be distinct whenever we see 2 colors as being different. Now, built into this entire scenario is the fact that we only have 3 kinds of color receptor cells in our retina. So there's a huge number of different physical spectra in the real world. And a few moments ago, I characterized that as having 31 channels. There's a huge number of those spectra which map into the same set of RGB numbers. It's this 31 to 3 mapping that I referred to in the introduction. So it's a many, many, many to 1 map. And that mapping to a color scientist is known as metamerism. So there's a lot of degrees of freedom that you've got in choosing what the spectra might be to produce the same color. So we'll come back to metamerism, but it's very much wrapped up in this notion of a 31 to 3 mapping. Now, to amplify those 3 curves and overlay them on the same plot, here's the graph. And I'm taking a little bit of liberty here in coloring the lines of this graph red, green, and blue. A color scientist would prefer that you called these channels long wave, medium wave, and short wave. And in a practical camera, from one point of view, you think, if I want to get perfectly accurate colors, this is how the camera should work. And that is theoretically correct. But in practice, there's several engineering and image quality problems associated with using curves like this. The main problem is that these curves overlap dramatically, and that's got noise implications. So if you were to build a camera that had these curves, generally speaking, you would get noisy pictures. And usually in industrial applications in digital cinema and HD, we're willing to take a little bit of color inaccuracy, a little bit of color mapping errors, if you like. We'll live with that to get better noise performance. So in a real camera, we typically move the peak of the long wave sensor further out to make those curves overlap a little less. But this set of curves is very closely representative of human vision, and we'll work with that. Now, there's a good reason to map this LMS system into a different system that turns out to be the core color system for color science. And the reason that it's useful to make that mapping is it's very useful for color science to have one of the three channels corresponding to the spectral properties of our lightness sensation. Now, we'll get into exactly what the word lightness means in a technical sense a little bit later, but for now, just keep in mind that these graphs and this process that I'm describing in this section is treating color quantities in linear light form, or to use the contemporary digital cinema term, scene referred, or it's scene linear. And lightness, you'll discover later on as we go through the remaining sessions, is a perceptual quantity that's been run through a nonlinear mapping. So keep in mind these are linear light signals. And it's really useful to have a linear light signal which represents the lightness sensation. That linear light signal is called luminance. And it comes in two flavors, absolute and relative. Absolute luminance has got units of candelas per meter squared. Because that's a lot of syllables, candelas per meter squared, and because it has a very complicated typography, CD.M superscript -2, that's all too complicated. Let's just call it nit. And nit derives from the Latin word nitere, to shine. So we'll call it nits, we'll give it a symbol NT. And another unit for absolute luminance is Foot-Lambert, but for reasons which I'll describe later, I don't like using those units that are based on imperial feet measurements. I believe color science and radiometry and photometry is much easier if we just use a single consistent set of units. Those are the SI units, the metric units. And candela per meter squared is formally correct. Nit is just the casual name for candela per meter squared. Now, all of that has got to do with absolute luminance, and absolute luminance turns out to be really important in image science, digital cinema, and HD, but often we'll want to deal with relative luminance where we pick a reference value of reference white. And maybe we give that an absolute luminance reference. In the case of HD studio work, that would be 100 nits white. Now, unfortunately, that's not standardized in an international standard. It should be. I hope it will be soon. But in the meantime, I recommend that you set your HD mastering situations with reference white at 100 nits. Relative luminance, then, on the display side turns out to be proportional to that. So let's give relative luminance a number from 0 to 1. And those are the numbers that I'm using on the y-axis of this chart. Now, we have been talking about the LMS curves of human vision. We're going to transform those through a reasonably simple mathematical transform. It's a 3x3 matrix multiplication, or if you like linear algebra, you can call it a dot product. And if you're a mathematician, you can call it an affine transform. All of those mean the same thing. We're going to transform so that one of those components mimics the luminance sensitivity. And that's very fundamental to human vision. When we do that transform, though, we're going to find that because we're mixing one channel to the other in a certain special ratio, one of those other components is going to pop up and make an extra bump. So here we go. We're going to do the transform from LMS to the CIE color science fundamental components X, Y, Z. Here's the transform. So now, as I mentioned, there's an extra little bump in the X bar component, or the X bar weighting curve, which produces the big X tristimulus component. This extra bump is not a feature of the cones of the receptors of human vision. It's a consequence of a mathematical process involved in the transform. And you'll notice that the middle wavelength component now broadened out. That's the weighting curve of luminance. The other two components are that they have some luminance component in them, but they're really talking about color components different from luminance. Now, up on the title of this slide, I'm showing you the notation for those curves, those weighting curves. They're called X bar, Y bar, Z bar. And you can think of the bar on top of the X as being this weighting over the spectrum from 400 to 700. When you take a spectrum of those 31 numbers that come from your measuring instrument, you weight it by those numbers. It's simply a weighted sum across the spectrum. You get a number. You do that 3 times, you get big X, big Y, big Z. So the case of the letters, little x, little y, or big X, Y, Z, that matters. It's part of the notation. Now, I've been showing you these diagrams in a manner that could be implemented in a real camera by optical filters having characteristics like the LMS curves, or maybe like the LMS curves with the long wave component shifted 30 or 35 nanometers toward the long waves. But you could also interpret this arithmetic in a linear algebra sense, where you form X, Y, Z components by doing a 31 by 3 dot product. Now, I'm pretty comfortable with linear algebra. Many of you are comfortable with linear algebra. This is one way to do it. And arithmetic like this is built into color calibration packages, either calibration of a camera or, more commonly, calibration of a display or a projector. So you can make these X, Y, Z numbers using linear algebra, and when you do so, you get 3 quantities. Of course, it's difficult to plot in 3 space because we generally have 2-dimensional pieces of paper. So it's useful for industrial purposes to have a color mapping that basically collapses those 3 color coordinates onto 2 coordinates, absent one of them. And the one that we can eliminate for the purposes of talking about color is luminance. So the color scientists, and even in 1931, the CIE devised a little bit of arithmetic to factor out the luminance component and leave 2 other components which are in essence pure color in the absence of luminance. So we do that arithmetic like this. And again, case matters, uppercase, lowercase. So we take big X divided by the sum of big X, big Y, big Z. And that calculation in mathematical terms is called a projective transform. It's exactly the same mathematics that's used to collapse depth when you portray perspective. So it's like division by the depth value. Here we take the depth value to be this big X plus big Y plus big Z. When you do so, you form a chromaticity coordinate, little x. And there's a comparable calculation to form little y. Now, you may be wondering, why didn't we form little z? And the answer is, well, could have done, but that's not the way they did it in 1931. And there's no need to form little z as well, because the mathematics of this transform makes only two of these quantities necessary. The third is implicit in the other two. So this is the math that goes into CIE little x, little y chromaticity coordinates. And it's very easy to reverse out of that. These are the equations that you need. So ideally, oh, and by the way, then we keep the big Y luminance, relative luminance, and ordinarily, though, we don't plot it. We're going to plot little x, little y, and we're going to project all the big Y values onto the same plane. Now, we're not going to take slices. It's very much a projection or a collapsing of 3 dimensions into 2. You can undo it this way. Some of you might have expected to see a little z, or a little z in this position, but you don't have to convey the little z. It's equivalent to 1 minus little x minus little y. Now, having done that, we've got little x, little y chromaticity coordinates. Now we can plot. So those coordinates are plotted on the famous CIE chromaticity diagram, which takes the shape of a horseshoe. And if you start with a fully monochromatic, very narrow band light source, for the sake of argument, we can say it's a tunable laser, and we start at the long waves, which at some point will appear red, let's say around 700 nanometers, and we sweep that laser down across the whole visible spectrum, ending up at 400 nanometers. When we do so, the path in little x, little y coordinates that we traverse is this path. This is called the spectral locus. And when you move that laser back and forth across the range 400 to 700, something very interesting happens with respect to human vision. You don't get purple. Purple is only produced as a sensation within your visual system when you're exposed to shortwave and longwave energy, not much in between, or nothing in between. So in the chromaticity diagram, this bottom section is called the line of purples, and it's not produced by any single concentrated wavelength. It must have some long and some short wave at the same time. And there's several physical phenomena that create colors, such as oil slicks and rainbows. They don't have purple. But if you have a mixture of long wave and short wave, you can create mixtures along this line. Now, there's no unique perceptual or physical definition of white. There is a mathematical white which is useful for computational purposes. Just pretend that we had energy equally distributed across the whole spectrum, 400 to 700. And we give that a name, illuminant E, E for equal energy. But in fact, you can never find such an illuminant in practice. If you did, it would have chromaticity coordinates 1/3, 1/3. But in practice, a variety of different illuminants are possible. And a little later on, we'll get to what those illuminants are. And I have a favorite, and you probably know that favorite. It's illuminant D65, but let's do that a little bit later on. Now, if you want to sketch that horseshoe shape on a napkin, the way to do so is to start with this diagonal line at minus 45 degrees. In other words, start with the 1 minus x line, and a large portion of the horseshoe is tangent to that line. I've explained the spectral locus, which is the path traversed when you sweep a single monochromatic source from 700 down to 400. I've explained the line of purples, which is mixtures of long wave and short wave. I've explained that white is somewhere in the middle of the chart, but it's up for its standardization exactly where it is. And finally, there's an important and interesting portion of this chart called the black body locus, which is the line that's traversed in XY coordinates of, let's just say, the common illuminants. Normally, most of the sources of illumination that we use for capturing imagery, or even for living in ordinary life, the illumination is obtained by heating up something so that it radiates photons. And Max Planck won the Nobel Prize for work that he did in the 30s, figuring out exactly what the spectrum would be heating an object up. It's called the black body spectrum. And that spectrum depends upon the temperature to which you raise that metal or that gas. And we'll talk later on about the details of the black body locus and how it relates to Max Planck's concept of temperature. So those are the features of the chromaticity diagram. And we use this diagram extensively in the science of color imaging, but its use is not limited to imaging. Here's an example of a standard that's promulgated by the CIE, which dictates the standard colors of signal lights. Now, honestly, I don't have a copy of this standard myself. As far as I know, the standard really applies to railway signals. And one of the reasons that the CIE standardizes those is that the railways, I'm thinking Europe, go from country to country to country. And you'd like the signals to be the same colors in different countries so that the train crews recognize what their action is supposed to be. So a red signal light in the railway has got to live at an XY chromaticity coordinate in this region. A green signal lives in a region like this. A yellow signal for caution lives at these coordinates. In railways, you can have a white signal, even though we don't use those for traffic signals for cars. And there's a blue signal standardized in this standard. In railways, I guess they use blue. In Europe, flashing blue light is a police car. In Canada, flashing blue light is a snowplow. I don't know, figure that out. But there's various colors of lights that are just bounded by their coordinates in CIEXY space. Now, I'm hoping that you're looking at this diagram and you're thinking to yourself, wait a minute, how can it be that red lights are in this little region here that's like a Manhattan city block, and green lights are this huge area in this part of the diagram that's like the backfield of Kansas? Why is the green area got an area of 50 or 100 times the area allocated for red? And the answer to that question is basically this diagram is firmly rooted in physics. It has this perspective transformation where you take the big X and you divide by the big X plus big Y plus big Z. So there's that element of distortion, if you like, that takes place in that perspective collapsing. But apart from that, there's really no perceptual phenomena that have been folded into this diagram to make it perceptually, well, I'll use a special word here, uniform. For many purposes, we'd like to have a color coordinate system where if you go plus or minus one count on any of the three coordinates, you produce approximately the same perceptual shift in the color. Such is not the case with this diagram. And we'll be heading toward discussing other color systems where that property holds true. Those are the perceptually uniform color systems. And obviously, little x, little y coordinates will not achieve that end. Nonetheless, this is the set of coordinates that's most closely associated with linear light scene-referred color values. So this is the one that we generally use to characterize imaging systems, both cameras and displays. Now, we've come to the stage where we've got three numbers, and for the purpose of color science, I'd like you to think of those as being big X, big Y, big Z. But there's a couple of different systems that are related to X, Y, Z with a simple 3x3 linear light transform. And those, I can tell you two of those systems right now. One of them is the LMS system, which is the basis for human color perception. Another set would be RGB, where the RGB values are linear light. Now, it'll work out later in the course that these 3x3 matrix transforms are exactly the transforms associated with the input device calibration transform, the IDCT, of the Academy Image Interchange Framework workflow. And we'll get to the details of those matrices in several classes from now. They end up being 3x3 transforms in linear light space. But let's for now just think of going to the color science native space X, Y, Z and thinking about how we can take those values and recreate colors at the other end of the system. So in between acquisition and display, we've got three channels. They could be X, Y, Z, they could be RGB, they could be LMS. Let's talk now, though, about taking three numbers and recreating colors at the back end of the system at the display. Now, there's two different ways that we can do that, and they're dramatically different systems. First, we'll talk about having a display system that can produce three different spectra driven by three different values where the power is variable in each of those three channels. And it's going to work out through reasons that will become clear in the next 5 minutes that the best colors to use as the basic fundamental elements of the mixtures, those are the primaries, the display primaries, the best colors in an additive system are going to look red, green, and blue. So here I'm giving you a rather old-fashioned example of the spectral power distributions coming from a Sony Trinitron cathode ray tube. So the blue phosphor generates optical power that has a spectrum like this. The green phosphor generates a spectrum like this. And the red phosphor generates a spectrum like this. Now, these are real measured spectra from a Sony Trinitron studio display. And you've probably noticed that the spectrum from the red phosphor is dramatically different in nature from the blue or green. And this is owing to the chemical composition of that red phosphor. Basically, in the 70s, the phosphor for red looked kind of like these shapes, but a new phosphor composition was identified that was much brighter, and that phosphor composition was adopted. It's basically a mix of two different phosphors, and they produce this rather unusual spectral signature. But from what I talked about 10 minutes ago, the phenomenon of metamerism in human vision means the only thing that really matters as far as our human color perception is concerned is how much power falls under each of those three curves. The particular nature of where the power lies within each of those curves doesn't really matter. That's the magic of metamerism. So the fact that there's two narrowband emitters in the red phosphor of a CRT doesn't matter. Now, the key part of color mixture is we vary the amount of blue, vary the amount of green, and vary the amount of red, and form a mixture. And that mixture can be described mathematically or in physics as simple addition. So we call this additive color mixture. And the implications in the mathematics we'll talk about a little bit later on. That's the first way to do color mixture. The second way is much more complicated and also doesn't really matter for us today in HD or digital cinema because additive mixture encompasses all of the display devices that are useful to us. But I find that it's a good idea to explain subtractive mixture. First of all, that's how offset printing works. It's how inkjet printers work. It's also historically how motion picture film works. So it's very useful to have a rough notion of how subtractive mixture works, even though none of the systems we're using today actually require that. So let's go and spend a few minutes talking about subtractive mixture. In this case, the idea is we start with an illuminant which is rather uniform across the whole spectrum, 400 to 700. And from that rather uniform starting point, we remove energy at short waves, at medium waves, and at long waves. Now, I'm drawing this diagram as if we're removing the energy using colored filters. And in fact, the numerical data that I've shown here is the absorption curves of the dye filters which are formed into color print film when you develop the film. So these curves are characteristic of motion picture print film. So you remove some amount of shortwave light with a filter that individually would appear yellow. You remove some amount of medium wave light with a filter that individually would look magenta. And you remove long wave light with a filter that individually would look cyan. When you do so, you get spectral mixtures that look something like this, where the three bands are controllable. And loosely speaking, you can think of the yellow filter, the amount of filter that you deposit in the film controls the absorption, and that's really modulating the shortwave light or the blue. The magenta filter density or thickness is modulating medium wave or green, and the cyan filter thickness or density is modulating the long wave light, red. Now, what's complicated about subtractive mixture? Well, there's really two things. One is that mathematically or physically, things are being removed, but they're not really being subtracted. If I have a filter that transmits half the light, and I put behind that a filter that transmits half the light, I don't get zero. I get a half of a half, or a quarter. Mathematically, what's going on is not subtraction, but multiplication. So I kind of joke that we should call this multiplicative color. That's the math, that's the physics. But that multiplication is happening wavelength by wavelength. The other subtlety of this so-called, quote, subtractive mixture is that the yellow filter doesn't solely remove shortwave light, it also removes an unintended amount of medium wave light. And much more severe, the magenta filter that controls medium wave is absorbing quite a bit of shortwave light that's unintended or unwanted. So we call this the unwanted absorptions. And those absorptions make the color mixtures nonlinear and very difficult to analyze. Now, in the 50s and the 60s, there were mathematicians who tried to devise equations that characterized this nonlinear mixture. Today, we basically forget all that, and we characterize the mixtures using big lookup tables. And those lookup tables are the foundation of the ICC color management technology that's used on an everyday basis for inkjet printers. The ICC technology has turned out not to be very useful for really high-end digital cinema or HD. But in digital cinema and HD, we're just using additive mixture. So we don't need to go to the trouble of using big lookup tables most of the time. Later on in the course, we'll talk about the occasions when you do need to use lookup tables. So that's the basic subtractive mixture scheme. Now let's go and do a real demo of what additive mixture looks like when you're actually mixing real lights. You've seen the spectral diagrams corresponding to red, green, and blue additive mixture, but this is a real color science course, so we're going to show you real color mixture using a set of 3 spotlights: red, green, and blue. And I think you can imagine that if you start with green and add blue, basically we've got medium wave light, we're going to add short wave light, and you end up with light having short wave, medium wave, and no long wave. That mixture appears cyan. You might call it turquoise. Now, if we eliminate the medium wave light, start with short wave, and add long wave, short wave and long wave mixed together with not much in the middle gives magenta or purple. And both of those mixtures are quite intuitive. The troublemaking mixture is the next one coming up. If we have long wave light and you mix that with medium wave light, you get yellow. And it's not at all intuitive that that mixture would be yellow, because for perceptual reasons, the way our visual system is wired up, we treat yellow as a unique color, and we don't easily, or maybe at all, see yellow as a combination of red and green. In other words, we have colors which are bluish green, and we have colors which are reddish blue or bluish red, purple, but we don't have any notion visually of a greenish red or a reddish green. In fact, physically though, the mixture is yellow. And of course, if you mix all 3 components together, you get white. That's additive mixture.
Well, that was good, Charles. And I must admit, it's kind of a bit weird, the yellow thing about green and red, because I've always wanted to do that with the lights, but it never occurred to me that it's sort of a bit counterintuitive on the reddy-green colour, which isn't really the case, is it, with anything else?
It's very counterintuitive, and it's how vision works.
Yeah.
Vision makes that 4th channel that you wouldn't expect.
Yeah, there is so much about our eye that's relevant to some of this stuff. You know, like how even to the edge of your eye, you have different responses to stuff that's in the middle and all that kind of stuff. I'm wondering, though, that RGB stuff is, I guess, primarily it's certainly applicable to film in the sense that there are RGB layers in the emulsion of a piece of film.
It is absolutely related to that, although it's important to keep in mind that in terms of capture, the 3 channels are really captured independently. There really isn't
splitting
any.
It rather than mixing it.
It's either splitting or filtering out bands, but the channels are captured independently, so there really isn't any mixing going on in the capture.
Okay, well, I would say then that it's relevant to printing, but it isn't, is it? Because it's not an RGB. Because like if capturing it is separating it,
Yes,
you've got to put it back together again to project it.
and that's the mixing part.
Yes, but that's not an RGB mix per se.
Well, it could be. So you could build it, and we use them all the time, displays whose color operation is based on mixing the channels of light. And there the mixing is adding when it's light.
Yes.
But if you're using dyes...
Yeah, that's what I'm saying. In film, though, yeah, that's not the case, right? But then, so films are what? So it's not an additive of RGB.
Well, so we call that, quotes, subtractive, and I put quotes around it because mathematically what's going on is multiplication wavelength by wavelength.
Right.
And that mixing phenomena is then quite different from
because if
mixing
I had a
with light.
piece of film that had nothing happening dye-wise, I get white.
Yes.
And as I add stuff in, at some point I go to black.
It removes portions of the spectrum.
Right. So I'm adding dye to get me back from white down by filtering down. Okay, so now, well, could you even demonstrate that like you did with the... Is that
Well, yes, we could do that.
How?
We could do that. So the scheme would be starting with white.
Yeah.
and we can find a white diffuse source,
Yeah.
and then layer filter on filter on filter.
Okay.
And that would be mimicking layering die layer, die layer, die layer, just like a motion picture release print.
Okay.
So we
well,
could
it'd
do
be kind
that.
of fun to look. I don't know if you've got time, but in an upcoming class, it'd be good to have a look at that.
Let's give it a try.
Even though obviously digital capture and digital projection is what's happening, I mean, that's also related to print and a whole lot of things. And I actually have a principle that just because something is, obviously with Kodak restructuring stuff, we know that those things are somewhat in decline, but it's healthy to know about what's going on.
Oh, indeed. And I think that another important point is that we expect movies to look like film, even if they're not made with film.
Right.
So it's important to understand those film color mixing properties just to achieve the look of the picture that our clients, our customers expect.
Right. So somebody comes to me and says, I need that to look more filmic, more cinematic, whatever word they use.
Right.
And you know, okay, well, these are the properties of how the colours are working.
Right.
That is signalling that in much the same way a film grain would or, whatever.
Exactly. Okay. And it's perfectly reasonable in production, whatever you do that makes the image the way you want it to look is fine, but the process is a little chaotic if you don't understand the theory behind it.
Yeah.
So that theory of subtractive color mixture as used in motion picture print film, I think that's a valuable thing to know.
And just tangentially, I do have enormous respect for people that did or do color timing on films.
Indeed.
Because that process of color timing is actually very explicitly related to what we're talking about.
Absolutely it is.
Maybe you could just in 2 seconds, just give us what that color timer did and how limited their range of tools were.
Yeah, well, the timing in film was based upon adding little bits of attenuation to each of the 3 bands. And those little bits of attenuation are measured in terms of printer points. So one of the tools that digital grading has available is doing color adjustments in exactly those terms, because those are the terms that the colorists and the cinematographers understand.
But with a really different time frame, because I'd be in a grade, I used to do that, I had films that I color timed, and you'd be with the color timer, and you go, I think 2 points of magenta here. And it wouldn't be like, oh, okay, I'll just do that on the desk.
Right, it's
It'd
not
be
a
like,
dial.
come back tomorrow, and I'll see
exactly.
this print with 2 points of magenta.
Yeah, because what's happening is that in traditional film grading, the colorist would go back to the printer and drop filters in to attenuate the light according to those new instructions, but then pull another print and develop it and show it, and that's
in
the
fact,
time.
they would have that on a per scene basis.
Yes,
right? So you would
absolutely.
actually have this. I think they actually had it. I'm pretty sure this would happen. You had a computer tape at some point
Yes.
that controlled just the mechanical.
That's exactly the case.
Filtering. So you
Yes.
color time the whole film. It was a series of per cut. What do they do on dissolves?
Well, there's a little dissolve in the advanced machines.
Yeah.
There's a little dissolve code on the paper tape that says when to start the dissolve and how long it takes.
But I mean, how do they do that if they were actually putting filters in?
Oh, the mechanism in the printer is basically a rotating device that attenuates more or less light.
Okay.
So you can drive that attenuator slowly to cause a shift over a period of time.
Yeah, of course you could always. I mean, well, I guess they were doing this when they would, because I know in optical printers you'd like run the film,
Yep.
and then you'd run it down, back up the film,
Yeah.
and run it back up again. So
Well, you can do the same thing, but
Yeah.
of course, with digital technology, this all becomes easy.
yeah, it totally is. But having said that, I mean, how many times have you been? I mean, I've certainly been in a suite where somebody has said, who's old school, like a director, who said, "I think we need a couple more points on that."
Mm-hmm. Well,
and
that's
it's nice to not sit there and go, "What?"
that's the reason that even modern practitioners need to understand the historical techniques.
So just in finishing up, you're going to be available in the forum. So if people have got questions about, I've got the
Indeed.
advantage of being able to ask you questions right here. But if people have questions,
I'm here. I'm participating.
And so please fire those off. Charles is trying to answer them. I'll contribute if I can. Maybe I can't. And thanks for starting the course off so well.
Oh, it's a pleasure.
We'll
Thank
see you guys next week.
Okay.